Okay, now we will start chapter 10. So the first thing we want to do, so we already study correlation and regression in chapter 2, but in this chapter, we will know how to apply regression, correlation and regression. So we will have to take 10.1, which is correlation, and then 10.2 is how to apply regression. So we did say that correlation, just we do correlation to study the relationship between two variables. And we did say if we want to study the correlation, the first step we want to do to just do the scatter plot. So if we did find somehow linear pattern, though, then we can go study the linear correlation. So the linear correlation study the relationship if there is or is there any linear relationship between those two variable. So when we do study the scatter plot, somehow we will find the scatter plot like this, maybe, right? So in this case, we can say that, okay, there is a relationship between those two variables, and this relationship might be linear. So then we go try to find numerically how the value of that linear correlation. So the linear correlation, we have two. So R, which is linear correlation for sample, and then maybe rho, which is the linear correlation for population. Remember that we all the time we did say we use English letter for sample, which is we call it statistic, and we use Greek letter for population or parameter population, and we use this statistic to estimate the parameter of the population. So now this is the scatter plot. So if you look to this one here, we have the value of R. R equal 0.859, and clearly here we can say this is linear, and this is positive relationship between those two variables, right? Why? Because as one of the variables increase, the other one will increase too. So this is, we can say this is a strong positive linear relationship. So linear because we can see clearly that we can about this line, right? And then strong because of this value, and positive because of this sign, positive. R equal to positive 0.859. Remember in chapter 2 we did say R is between -1 and 1, and we did say as we get closer to 1 or -1, the relationship will be stronger, and as we get closer to 0, the relationship between those two variables get weaker till we get R equal to 0. When R equal to 0, we say that no linear relationship. No linear relationship between those two variables. Remember, we can, if R equal to 0, we cannot say no relationship between those two variables, but we can say that no linear relationship between those two variables. Why? Because it might be some relationship, but that relationship not non-linear, okay? So for the second example here, you can see that this is a negative relationship, right? Because as one of the variable increase, the other one will decrease. So for looking for this one and go back to this one, do you think what correlation is stronger without looking to the value? So clearly the second one here is stronger. Why? Because the distance between the straight line and all these dots is closer. So if the dots closer to the straight line, that's mean the relationship must be stronger. Okay, let me ask this question here. If we have a relationship like this, and we have a straight line, and all these dots here, what do you think the relationship? So for the first one, the relationship is positive. As one increase, the other one increase too, so positive. And then it's linear, right? Because it's clear that all these dots on the straight line, so it's linear. And then what about strong? Can we say this is strong? Yes, it's strong. And then what else? What do you think the value of R here in this case? In this case, the value of R will equal 1, exactly 1. Why? Because no error. In this case, this straight line is the same as the population line. So in this case, R will equal rho will equal to 1. Okay, but if you go look to this scatter plot now here, it's clearly that no relationship between those variables, right? Because we cannot represent this data as using any straight line, right? So this is no, from scatter plot, even we can say that, okay, no correlation between those two variables. But just using the numerical value this, we cannot say that no relationship. We can say no linear relationship. But from scatter plot, we can say that, okay, no relationship between those two variables. So if we want to study the correlation and we did scatter plot and we did say scatter plot like this, don't waste your time and go and calculate this value, because it's clearly that value it will be really close to 0. So now what about this one? So if you look to this one, it's somehow, it can represent it as a curve, right? So this one is a relationship, but it's non-linear. So if we represent this as a linear, still we might get line something like this or something like this, right? If we don't have this value, might be the relationship or this value of correlation, it will be higher. But this value, it will make this a straight line going like toward it a little bit. So instead of getting a straight line like this, maybe you'll go like this. And that's why this value is very small. Okay, now so for the form of the relationship between those two variables, we have 1 positive relationship, 2 negative relationship, 3 no relationship, 4 non-linear relationship. Okay, so if we got maybe the first and the second case, then we go and try to find the coefficient correlation R. Okay, so the linear correlation coefficient R, which is we use this to find the linear relationship between two variables in a sample. So R, and we say rho for a population. So rho to study the relationship in the population. Okay, so now, yes, to find the objective of calculating R, to find if there is any linear relationship or any linear correlation between two variables. So what we need to calculate correlation, we need the sample size n. And remember, in each value of n, we have pair of data. It will be xi and yi. So the values, it will be something like this: x and y. Some values here must be numerical values and some values here, and trying to study the linear relationship between those two variables. This summation. So now if we have, for example, x1, 2, 3, then summation of x will be just this summation. It's 1 plus 2 plus 3 is equal to 6, right? And then summation of x square, we have to take the square of each value of x. 1, 2 squared is 4, 3 squared is 9 first, and then sum them up. So that then summation of x square in this case will equal to 14. And then summation x square, it will be different. So this is summation x square. It will be just summation x with 6 square equal to 36. But summation x square equal to 14. So remember that summation x square not equal summation x all square. This is really important. Many students get confused between those two values. And then we have this value x summation of xy. So this one is we take for each single value. So we have x and y. So 1, 2, 3, and maybe 2, 4, 6. And then we want to take the summation of xy. So xy. So we multiply those values. So the first one will be 2, and 2 times 4, 8, and then 3 times 6 is, I don't know, 80, right? If my math is good. And then, so this is the summation, which is a 28. So summation xy will equal to a 28. Okay, and then remember, we did repeat this now many times, the the sample correlation. So the linear correlation coefficient for a sample. And then this is, we call it rho. It's maybe like this, rho. Rho is the linear coefficient, linear correlation coefficient for a population. Okay. So now to calculate the correlation, we must confirm 2 things. One, the sample of paired XY data is simple random sample of quantitative data. So we must have a numerical data. So the values of X and Y must be numerical. And how we did choose those values? Random, at random, must be at random. And then also we must do the scatter plot. We must examine if the scatter plot, and we must confirm that we have somehow linear pattern, so we can study the linear correlation. Also, if we have any outliers, we must remove those outliers first, right? Because the outliers will, I mean, the value of correlation will be sensitive to outliers. So if we have check outliers, if we have outliers, remove them first, and then we can study the correlation. Okay, so the formula for correlation, we can use this formula. R equal N summation XY minus summation X. Or you can use this formula. For me, I like this formula more. R equal to summation XY minus N X bar Y bar divided by the square root of summation X square minus N X bar square, and then the same for Y, which is summation Y square minus NY bar square. I will use this formula because this formula, it's easy to use, okay? Remember, X bar is what? X bar is summation X divided by N, and Y bar, it will be summation Y divided by N. So you can find easily, you can find X bar and Y bar if you have some sample of data. Remember this part here in the top, we just call it SXY. and this one here, we call it square root of SSX. Maybe you'll find it in some books like this. It will be this one, summation of SSY. So R basically equal SXY divided by square root of SSX times some SSY. Might you see it somewhere like this, okay? So now if you wanna also, you can find this R squared using Z value, since remember, Z of X will equal to X minus X bar divided by sigma or S for X, and then ZY will equal to Y minus Y bar divided by SY. So you'll find ZX and ZY for all data set, and take the summation, divide all those values in minus one, okay? So, and then if we have a correlation, we round this correlation up to 3 decimal places. So if you get the value of correlation 9357, maybe this is, it will be 0.936, right? So 3 decimal. Okay, so now if you want to do find the critical values for correlation, we will use B value. So B value must be less than or equal to alpha. Then we can say that, oh yes, we have a linear correlation. If this B value is greater than alpha, then we say that no, we don't have a proof that this relationship is really linear between those two variables. And if you remember, alpha is the probability that we will fall in type 1 error. This value usually 0.05. Okay, and then we have the table. We can use the value of a table, or we can use easily, we can use technology to find those critical value, right? So it will be like something like this. So we have, remember, the value of correlation between what? From -1 to 1, and here we have 0. So right, and we will get just 2 values. Those 2 values, we call them the critical value. So here it will be the critical value. Let's say R critical. It will be one by positive and negative. So if we got a value here or here, when we calculate correlation, then we say that, okay, yes, we have a linear relationship between those 2 variables. But if we have the value here in between, we can say that no linear correlation between those 2 variables. And then here, remember, the value of correlation is between -1 and 1. Okay. So now, if we change the other thing here, we have, if we multiply our random variable by any number, or divided by any number, and then we go calculate R, the R will not change. R will not change if we change our random variable to different scale. Okay, and then what else? So now, when we remember that when we study the relationship between those 2 variables, we cannot say this is basically independent or this is dependent variable. So those 2 variables, we can change them. It's taking X first or Y first is the same. So when we do the relationship, if we put X here and Y here, that's okay. Or if we put Y here and X here, it will be the same relationship. It will not be It will not change, okay? So the value of R, it will be calculating how strong the relationship between those two variables, right? So we say as this value gets closer to 1, the relationship, it will be stronger. As it get closer to 0, it will be weaker. But when R equal to 0, we say no linear relationship between those two variables. And then we did say also R is sensitive to outliers, right? Y is sensitive to outliers. Why? Because as you see in the formula, when we calculate the R here, we use those values. We use X bar, we use Y bar, and those values is very sensitive to extreme values or outliers. So that's why even the correlation will be too sensitive to outliers. So let's see this example now. So now here we have 5 number. They said use technology to find the value of correlation coefficient R of the data. So we have R, we have some values. So let's see here. Using technology, so remember, if we want to use this value, so imagine this is X and this is Y. So we have here X and we have Y, right? And then R here, we did say R equal to summation XY minus NX bar Y bar divided by summation X square minus NX bar square, and then summation Y square minus NY bar square. So what we need here, we will have the summation, right? And then we need XY, and we need X square, and we need Y square. I believe by this time you know how to find those values, right? So we have, for example, 5, 6, 4, 4, 5. Then here 6, 9, 3, 2, 11. So the first one 30, and so on, right? So X squared, this is 25. This is 36. This is 16, 16, and then 25. So this value here, it will be summation of X squared, and so on. But using technology, let's say using the stat disk here. So we did find R equal 0.794, okay? And this value here, let's do it here. So we did say this is -1, and this is 1, and here 0. And then look to those critical values here. So the critical values from -0.878, right, to the same here, it will be positive 0.878. So now any value of correlation here, we said, yes, we have a linear correlation between those two variables. But if we have values here in between, we say no linear correlation between those two variables, right? So let's check our value here. It's R here equal to 0.79. It's somewhere here, 0.79. Yes, 0.79. It's, I mean, the number is close to 1.8, right? But since the sample size is small, then that's why we have to have a very big number of correlation to say that, okay, yes, we have a correlation. So look, if you look to the B value here, this B value less than 0.05. So if we have B value less than alpha, we couldn't support that we have relationship or linear relationship between those two variables. Here, then what? We don't have linear relationship between those two variables. Or the it's not enough to say that we have a relationship between those two variables, right? So let's go here and check how does this work. So now this is how to find x squared. So 5 squared is 25, 6 squared 36, 4 squared 16, 16, and then 25. And then for y squared 36, 9 squared 81, 3 squared 9, 2 squared 4, right? And 11 squared 121. And then when we multiply them up, so this will be 30, and 6 times 9, 54. So we got all those summation, just come and apply them here, right? So you can say, okay, R will equal to summation xy minus n x bar y bar divided by summation x square minus n x bar square times summation y square minus ny square. And then let's go. Summation xy, it will be 159 from here, right? Minus n equal to 1, 2, 3, 4, 5. So n equal to 5. So we have 5. And then x bar is 24 divided by 5. And we have y bar, which is 31 divided by 5. You can keep them like this, or you can summarize them. And the same here, when you get this value, you will find it. You will find this value. So you can use this formula, or you can use this formula to calculate the correlation between those two variables, okay? Okay, so then here, let's see what we want to do here. Okay, it's easier to understand how our work. The variable of x is okay. So if we use z value, so I did this one. So now finding z value. So for each value here, so let's see. So x bar equal to 4.8, right? So for each single value, so let's take for the first one here, it will be z x equal to x minus x bar divided by sx. So for the first value, so let's see, we have x minus x bar, which is 4.8, and we have sigma, which is this one, the standard deviation, which is so let's keep it smaller, 0.83660 maybe. So now for each single value, it will be, the first value, it will be 5, this one, 5 minus 4.8 divided by 0.83666, we will get this value, which is 0.239. And then if we did use 6, just this exactly the same, but here we will put 6, then we will get this one, and so on, okay? If we find all those values for x and for y, and we multiply those values together, and we take the summation, we will find this value. So R will equal to summation zx times zy divided by n minus 1, which is equal 3.1791 divided by 5 minus 1, which is equal to 4. Then you will find this value of the correlation, which is exactly the same value we did find. Okay. So now, as we mentioned, that when we have a sample size, small sample size, we need really big a number of this correlation to say that yes, we have a linear correlation. So let's use the same example, but now with n, instead of n equal to 5, with n equal to 23, which is those values. In your book, you will find them in chapter 10. Yes, table 10, 10.1, I believe. Okay, so and then let's see. If we did check the scatter plot, which is the first step we want to do here, yes, we can somehow see that we have a linear relationship between those two variables, right? And we expect that relationship, it will be somehow strong. Yes, we do have some values which is far enough from this straight line, but most of those values it's not far from the straight line. So we expect this relationship, it will be strong. So this is positive or negative? Yes, it's positive relationship, but because as one increase, the other one increase. Yes, it will be linear because you see that linear pattern, and this for sure, it will be positive since we have as one of those four variable increase, the other one will increase too. And then we can check the B value for this one. If B value less than 0.05, yes, we support the claim that we have linear correlation. If B value greater than 0.5, we don't support that claim. Okay, so let's see here now. Let's me, I believe I can show you how to do it, this one using technology. So here, if we go to data, so go to StatDisk, and then the second book here, this is our book that we will use, right? Elementary Statistic, the 13th edition, and then go to example number 16, this one. So this is the same example in your book, and we will use those two variables, the chocolate and Nobel, right? So let's see, choose here. One of them, no matter, and then the other one will be here, and then we find the relationship. So significant here, the alpha we use is equal 0.05. So now look here, how many values we have? The sample size equal to 23, and the degree of freedom is 21, because why 21? So n minus 2. Why n minus 2? Because we know the value of x bar and y bar. And then now look to the value of this correlation, 0.801. Okay, and the critical value 0.4. Why this value is small? Small because we have a larger sample size. And then look to the B value almost equal to 0, right? So we have, we can support that we have linear correlation. So let me go back now here. So this is the value here, right? This is the same value. So let me put it here. So this is -1, and this is 1. And here we get 0. And then we did say here, the critical value, which is 0.413. And here -0.413. So if we have values here or here, we can, yes, we have linear correlation. So our value is here, which is 0.8, right? So now, yes, B value is, so B value less than 0.05, which is the value of alpha. So we can support the claim that, yes, we have a linear relationship between those two variables, right? Yes, it is here. So here, any value here or here, we have a correlation. This one, we should say we have no linear correlation, because we cannot guarantee that the relationship is still, we have a relationship, but this relationship is not a linear relationship. So in our example, we got this one, which is 0.801, which is, we can say, yes, we have a strong positive, linear relationship between those two variables. Okay. Okay, so we explained this one with the critical values here. So here we have correlation, we have correlation. Here we have no linear correlation. Okay, and then let's see here. Yeah, they repeat it again. I don't know why. So I think we already explained everything here. So here, explained variation. Okay, so now if we have the value of R, which is between, sorry, R, which is between -1 and 1, if we square this value, we have R square. And R square is the value that how much the explained variation in our relationship. Okay, we will talk about this one more in regression. Here we shouldn't study it because in this one we can say, I mean, R square is how much variation of the dependent variable can be explained using the independent variable. But you know, when we study correlation, correlation does not mean causation, so we cannot say this is independent and this is dependent variable. Okay, but yes, when we study correlation, this value will be how much variation can be explained using the independent variable. How much variation in Y can be explained using the independent variable X. Okay, so if we did find so here here R squared is 64%. So we can say, okay, R squared equal to 64.2%. So 64.2% from variation in one variable can be explained by using the another one here. Okay. So I don't know, it shouldn't be using here. Again, it should be used when we use the study the regression. So again, correlation does not mean causation, but here, yes, we calculate this value, so we can say, okay, about 64% of variation in number of noble can be explained using the linear relationship between chocolate assumption and the number of noble. Okay, and then yes, if we have 64% of variation can be explained, then this one 36% of variation cannot be explained using the chocolate, and might be we have different factors that we don't study. So either different factors that we didn't study or sampling error. Yes, here then correlation does not imply causation, which is we already did explain. So common errors involving in correlation. Yes, so so the first one we did say that many times they say confuse that use correlation imply causation, which is not right, and then using the data based on averages, so we don't use just only one variable and watch that variable, I mean that observation how it changed, so we use it in on average. Okay, and then yes, when we are equal to 0, that does not mean we don't have correlation between those two variables, because might be a non-linear correlation between those two variables. And that's it for first session. I'll see you in the next session. Bye.